let me fill up a few gaps in the last lecture. So, for example, this was I had discussed this card game, bridge game. There was an example number 2.7, which was talking about a game of bridge in which 26 cards have been dealt to people, to the players A and C. So, remember there were 4 players A, B, C, D. So, 26 cards have been dealt to the players A and C with 7 clubs. So, we wanted to compute the probability that player B gets 4 clubs, right. Now, I was trying to say that this can be I was trying to show this as an example of computing a conditional probability, that is already 7 clubs have been dealt to players A and C. So, what is the probability of getting B getting 4 clubs? But now I wanted to then show you that, and of course, we solved out the problem. I told you that this is the probability, but then it was not possible to explain this through the conditional probability argument. So, therefore, I just want to tell you that there are other ways of computing this probability, and that is by reducing the sample space. So, now instead of taking the distribution of 52 cards to the 4 players, I am just reducing the sample space, because 26 cards are now left, out of which 6 are clubs, because 7 have already been distributed to players A and C. So, then this is now your multinomial distribution. So, what you are saying is that out of 6 clubs B should get 4, and then from the remaining 20 cards he should get the other 9 cards. So, that way he gets 13 cards. So, this is the number of ways in which he can get 4 clubs out of 6 and 9 cards out of the remaining other 20 cards. So, this is the number of ways in which he can this can happen, and the total number of ways in which he can get 13 cards out of 26 is 26 choose 13. So, this is the actual probability, and this we can get by reducing the sample space. So, this is another technique which is very helpful, and at times you can very easily compute the required probability by doing this, right. So, you do not have to always go through the formula, the actual formula. You can always play around with alternative ideas also. Okay. Now, remember I asked you to construct examples when we were talking of independence of 3 sets, right. And in that case, I showed you that there are 4 conditions which have to be satisfied before you can say that the 3 sets are independent. And then I asked you to construct a counter example to show that, suppose the first 3 are the last 3 are satisfied. That means, pairwise if we choose any 2 sets from here, they are independent, they satisfy the condition of independence. That means, your probability of E intersection F is P E into P F, probability of E intersection G is probability of E into probability of G, and similarly probability of F intersection G is a product of the probabilities P F into P G. So, you can construct situations where, let us say, last 3 conditions are satisfied, but the first one is not satisfied. And so, I have been able to lay my hands on this example here. Suppose your sample space consists of these 4 numbers. So, where each number is equally likely, that means the probability of any number coming up as a result of the experiment has probability 1 by 4, because they are equally likely and there are 4 elements in omega, your sample space. Now, let us choose E to be as consisting of the numbers 1, 4, F to be consisting of the numbers 2, 4, and G 3, 4, right. In that case, you see, if you see the probability of P E, P F and P G is 1 by 2, because there are 2 numbers, totally 4. So, 2 by 4, again we are using the same concept, because outcomes are all equally likely. Therefore, I am using the m by n version of the probability, and so this is half for each of the sets. Then probability E intersection F. Now, E and F have only 4 in common. So, that is 1 singleton, and that probability is 1 by 4, which is the product of P E into P F. So, similarly, you see that the pairwise independence has been, you can easily verify that the 3 sets are pairwise independent. But when you write E intersection F intersection G, that again results in a single number 4, and so this probability is 1 by 4, but this is not equal to P E into P F into P J, which is 1 by 8. Okay. So, and therefore, now you get an idea, and you should try to construct one example of your own to show that you know, a pairwise independence of 3 sets is not enough to say that the 3 sets are independent, or 3 events. I mean, the 3 events are independent, right? You should be able to construct. And as I said that you know, extending this becomes little more cumbersome, and so we will leave it here only. Right. Now, exercise 2, of course, I have given you the corrected version. Okay. So, this is there, and question 10 in exercise 2, I want to revisit, because when I was reading it last time, I said that this needs a little thought, and so let us revisit the problem. So, actually you were given the data that a battery has a lifetime. So, there is a probability that the battery will last for more than or equal to 10,000 kilometers. That probability is given to be 0.8, and the probability that more than or equal to 20,000 kilometers, the probability was given as 0.4, and then that it will last more than or equal to kilometers, also a probability is associated with it. And you were asked to find that if you have bought a battery which is already run for 10,000 kilometers, what is the probability that will be running for more than 20,000 kilometers. That means, its lifetime will be more than 20,000 kilometers if it has already run 10,000 kilometers. So, this is a simple case of conditional probability, computing the probability that the lifetime. So, if I let L denote the lifetime of the battery, we are wanting to compute the probability, conditional probability of the event that the lifetime is more than 20,000 kilometers, given that it is already 10,000 that is, it is already 10,000 kilometers old, the battery, it has run that much. And so, by a formula, now when you take the intersection of these two, so obviously this is a subset of this, and therefore, the intersection simply becomes L. That means, you are wanting the lifetime to be greater than or equal to 20,000 kilometer, when it has already run for more than 10,000 kilometers, right. So, the intersection of these two would be this, because you want the battery to run 10,000 kilometers and you want the battery to run 20,000 kilometers. The intersection would mean that you want the battery to run for 20,000 for more than 20,000 kilometers, and so this is divided by the probability of this event, which is L greater than or equal to 10,000, and therefore, this is equal to 0.4 by 0.8, which is half. So, this is this. So, I just thought that if you have thought about the problem, maybe some of you have already done it, but then this is the right answer. Okay. We have talked of conditional probability, but I just thought that should formalize this in some more, in the sense that you see, we are defining now, given an event A, then we are computing the conditional probability of events conditioned on f, right. So, want to show that this is the function that you have defined here, the conditional probability function satisfies the 3 axioms of probability, and not too difficult to compute, to show, because the first axiom requires that this, for any event E, the conditional probability with respect to f must be within 0 and 1, right. That is the first axiom. So, here if you take probability E conditioned on f, then by definition this is this. Now, you see that E intersection f is a subset of f, right. This is a subset of f, and therefore, we have already shown, remember, after giving the axioms, we proved some propositions, and there I showed that if a subset is a subset of another subset, then the probability would be. So, that means, here probability E intersection f will be less than or equal to probability f, right. This because this is a smaller event, in the sense that this is a subset of this, therefore, probability of this is less than or equal to this. This we could easily show, right. Then and by definition of course, probability E condition F is non-negative, right. This is non-negative, this is non-negative. So, this is non-negative. So, therefore, the first axiom is satisfied because the P intersection F is less than P F. So, I divide by this is less than 1 and this is non-negative. So, first axiom is satisfied. Now, second axiom said that your probability omega should be 1. So, here for us, because we are conditioning on F. So, the corresponding axiom would be that probability okay. I should have sorry. This should be again the same thing. I have to say that omega condition on F. So, what will this be? This, and therefore, now when you take omega intersection F, this will be probability F this is equal to 1, right. Okay. So, therefore, probability F divided by probability F is 1. So, probability of omega condition on F is 1. So, the second axiom is satisfied, and the third one requires an EI intersection F divided by PF. Now, this I can write as, see here this is this, then because distributive law holds, this will go as this can be written as union EI intersection F, I belonging to I, this thing. Now, because EI intersection F are disjoint, since EIs are disjoint, right. I have taken a sequence of disjoint events EIs here. So, EI intersection F are disjoint, and so by and probability P, the probability function, the original probability function satisfies axiom 3, right. And therefore, this can be written as summation of probabilities EI intersection F divided by P F, right, which is equal to. So, this can be written as summation probability EI condition F, right, I belonging to I. So, the third axiom is also satisfied. Therefore, the conditional probability function is also a probability function, that is, it satisfies the 3 axioms. Okay. Now, again I just want to continue working, because conditional probability function is an important concept. So, again a little elaborated example that I would be 2 gamblers. Okay. Oh, here fine. So, this problem would be coming after I define for you the conditional probability. Now, I want to discuss the gambler's ruin problem, which is an interesting example of conditional probability, use of conditional probability. So, let us see there are 2 gamblers A and B, and they bet on the outcome of the toss of a coin. Right. Now, if on each toss, if H occurs, that means if the head shows, then A collects 1 unit from B, and if tail occurs, that means if T occurs, then B collects 1 unit from A. So, this is all a simple game. You toss a coin, and then if the head shows, A gets the money, and if tail shows, B gets the money from A. Okay. Now, tossing of the coin continues till one of them runs out of money. So, that is the gambler's ruin, right. So, one of them will end up with all the money, and the other one will have no money left. So, suppose total money is 15 units, I am just taking a number 15, you will see that through the solution it does not matter whatever the amount of money that they start with, and A has I units. So, that means B will have 15 minus I units with him. Okay. Now, tossing of the coin are independent events, and we are assuming that the coin is biased. So, therefore, probability H is P and probability is 1 minus P. Well, okay, we will also consider the case when P is half. Okay. Now, we want to find the probability that A ends up with all the money, and we have assumed that starting at the starting point A had I units of money with him, right. So, let E be the event that A ends up with all the money, and let P I denote the probability, because we are starting the game when A had I units. So, I am just denoting it by P I, which is the probability of E ending up with all the money, and A had I units to start off, right. Now, we have been using this technique very often, because when you are tossing a coin, your sample space is consisting of just h comma t, right, 2 points in the sample space. And so, you can write P e in terms of conditional probability p given h, and then that means now this we are saying that we are starting the game. So, the first toss of the coin either results in h or in t. So, this is conditional of E. That means, this is the probability of E. This is the event that A ends up with all the money starting with I units when the first toss results in head. So, this is that event, right. So, that into P h plus this is again the similar interpretation that A ends up with all the money when the first toss of the coin shows a tail, right. So, this is this into P t. Now, when the first toss of the coin gives you a head, then A collects 1 unit from B. So, therefore, the money at the end of this after the first toss A ends up with money I plus 1, right. And if the first toss shows a tail, then A will have to give 1 unit of money to B, and therefore, he will have I minus 1. So, therefore, if I, as I said in the beginning, I am denoting this by P I, because A had I units of money when the game started. So, therefore, this equation can be rewritten as P I is equal to P I plus 1, because this will be then the probability that now A has I plus 1 units, and we want to compute the probability that A ends up with all the money, right. And then this into P, probability of getting ahead. Then here A will lose 1 unit of money to B. So, it will be P I minus 1 into 1 minus P. So, 1 minus P we can also write as Q. Now, I can, since P plus Q is 1, I can multiply this by P plus Q and write this equation in this way, right. And then rearranging the terms, that means, see P I plus 1 minus P P I bring here, and P I minus Q I take to this side. So, I get this equation, right, and that gives me that P I plus 1 minus P I is equal to Q by P into P I minus P I minus 1. So, I get a recursive relationship between these P I's. Okay. And boundary conditions are that if P had no money, obviously, the probability of his ending up with any money is 0, because he will not be able to play the game, right. So, P 0 is 0, and P 15, because the moment he has 15, he has won the game, and so the probability is 1. So, P 15 is 1, okay, and P 0 is 0, right. So, therefore, now we use this recursion and we start with I equal to 1. So, when I is equal to 1, this will give me P 2 minus P 1 is equal to Q upon P, P 1 minus P 0. So, P 0 is 0, and therefore, I get this equation. Then when I put I equal to 2 in this recursion, I will get P 3 minus P 2 equal to Q by P, P 2 minus P 1, but P 2 minus P 1 from here is Q by P P 1. So, it will be Q by P whole square P 1, and so this way you can go on writing the differences. So, P 15 minus P 14 will therefore become Q upon P raised to 14, because whatever the number here, that is 1 less than this. So, the power of Q by P is 14 into P 1, right. Adding up we obtain. So, now I add up all these equations, then you see these things will cancel out in pairs, right, and you will be left with P 15 minus P 1, but P 15 is 1. So, this is 1 minus P 1 is equal to, and on this side Q by P you can take outside. So, it will be 1 plus Q by P plus Q by P whole square and so on up to Q by P raised to 13 into P 1, right. And now, this is a geometric series. I can write down the sum. So, this will be 1 minus Q by P raised to 14 upon 1 minus Q by P. Now, this is a finite geometric progression. So, therefore, it does not matter. The only thing I need is that I can do this if Q by P is not equal to 1, right, because otherwise I will be dividing by 0. So, if Q by P is 1, then P 15 minus P 1 you immediately get is 14 P 1. In the last equation you substitute Q by P as 1 everywhere, then and so from here you will get P 15 is 15 P 1, right, because P 1 gets added here, and therefore, P 1 is 1 by 15, and now you can easily compute your P 2, P 3 and P I. Okay. By going backwards you can compute your this thing, fine. So, we consider the case when Q by P is not 1, In that case, what we got from the last slide is 1 minus p 1 is q by p, 1 minus q by p raised to 14 upon 1 minus q by p using the geometric progression series sum. And so, if you take p 1 to this side, then you get this, and now you just simplify, and after simplification you will get that 1 minus q by p raised to 15 upon 1 minus q by p into p 1 is 1. So, p 1 is 1 minus q by p upon 1 minus q by p raised to 15, right. And so, the required probability, again from your recursion equations you will immediately get that required probability p I, that means when A started with I units of money, would be 1 minus q by p raised to I upon this, because that sum will be up to q by p raised to I minus 1, and so you will get this. So, you will substitute for p 1. So, 1 minus q by p will cancel out and you will get this, right. So, now if you want to find the probability that B ends up with all the money, replace P by Q and I by, so that means, right, because now for B the P is Q and the money that B starts with is 15 minus I. So, when you make these two replacements, you will again get the formula for computing the probability that B ends up with all the money, right. Okay. Now, again continuing with some more results on conditional probability. So, this is proposition 2.5. What we are saying is that suppose you are given that conditional probability of A given B is 1, then you can show that conditional probability of B complement given A complement is 1. So, here I could have also given this as an exercise, but I just thought I will show you some more ways of doing it, and then you can apply it to, for example, I think you can show that conditional probability of A complement given B will also be, you can compute, or okay, that will be independence, fine, right. No. So, right now just look at the definition. So, the conditional probability of A given B is given by this. Now, since this is equal to 1, it follows that probability A intersection B is P B. So, the moment you get this result, you can see that a probability A union B, which is written as P A plus P B minus P A intersection B, this will because this thing is 0, P A intersection B minus P B. So, it reduces to P A. So, therefore, your probability A union B reduces to P A, right. And therefore, when you take the complement of A union B, so probability of A union B complement will be 1 minus P A, which is nothing but P probability of A complement. And so, and then again by your De Morgan's law, we had seen that A union B component will be A component, complement is A complement intersection B complement. So, this probability is therefore, probability of A complement, right. And hence, your probability of B complement conditioned on A complement is this. Now, since these two things are the same, therefore, this reduces to 1. So, one can go on, and therefore, now the idea would be that you should get interested enough to try out many more results related to conditional probability, solve more examples. Okay. Now, final result on conditional probabilities. Now, this is conditional independence. Remember, we defined independence of two events if the probability of the intersection of the two events is equal to the probability of the product of the individual probabilities. Now, same thing gets extended. So, we say that E 1 and E 2 are said to be conditionally independent given that event f has occurred. So, if probability E 1 conditioned on E 2 intersection f is probability E 1 conditioned on f. That means, the occurrence of E 2, the same definition that we gave for independence of two events, occurrence of E 2 has no bearing on this probability, right. So, that means, when you condition it on E 2 intersection f, it is the same as conditioning on f, and E 2 has no role to play. Right. Now, in fact, so we will just write it out in a, so this is one definition, but you can come to a better result, and this is we say that E 1. So, therefore, by definition E 1 condition E 2 intersection f, this probability can be written in this way, right, and this is given to be by the definition of E 1 E 2 being conditional independent, conditionally independent, this is probability E1 conditioned on F, right. So, therefore, from these two you get that this probability is equal to E1 F, and this probability of E2 intersection F I can write as E2 conditioned on F into PF, right. So, this is the result, and this one also again now I can condition on F. So, this will be probability E1 intersection E2 conditioned on F into PF and this. So, PF cancels out, because remember whenever you talk of conditional probability with respect to an event, then that probability has to be positive, otherwise you cannot define it. So, of course, it is understood that PF is greater than 0. So, therefore, I can cancel out PF here and I will be left with probability of E1 intersection E2 conditioned on F is the product of the individual conditional probabilities, that is probability E1 conditioned on F into probability E2 conditioned on F. So, this is you just extend the original definition of independence of two events to in the same way. And so, I will take up now an example, a little elaborate example to show you the use of conditional independence. After defining conditional independence of two events with respect to the occurrence of another event, I will now take up this example. It may look a little complicated, but it shows good use of concept of conditional independence. So, here again this example I have taken from Sheldon Ross. Surprisingly, this book, I will give you the reference later on, has lot of new and innovative examples, and therefore, I am using quite a few of them here in this course. So, now consider the situation when there are k plus 1 coins in a box, right, and the probability of choosing the ith coin show there are k plus 1 coins in the box, and if I pick up the ith coin and toss it, then the probability of its showing a head, ith coin shows a head, is I by k, and I varies from 0, 1 to k. So, that means you can see that when I is 0, that means if you pick up the 0th coin, then the probability of its showing a head is 0, which means both sides must be tails. Then if you choose the if you happen to choose the second coin, the probability of its showing a head would be 2 by k, right. And similarly, if you choose the coin, the kth coin, if you choose the k plus 1th coin which has the number k, then the probability of showing a head would be k by k, which is 1. So, probably this particular coin, the k plus 1th coin, is having head on both sides. So, whatever it is, the situation is this. Now, a coin is randomly selected from the box and is repeatedly tossed. This should be repeatedly Ly. If the first, so let me just make the correction here. So, it is repeatedly tossed. Okay. If the first n tosses all result in heads, what is the conditional probability that the n plus first toss will also result in a head? So, that means, I pick up a coin at random from the coins which are there in the box, then I repeatedly toss it, and if the first n tosses have shown heads, then I want to compute the probability that the n plus first toss will also result in a head. So, let us see, we start finding out how to compute this probability. So, suppose C I is the event that the ith coin is initially selected, and this could be any of the 0, 1 to k numbered coin, right. Then f n is the event that the first n tosses resulted in heads. This is the, and then h is the event that we want. So, n plus first toss results in head. So, I want to compute the conditional probability of h given f n, given that f n has occurred. So, we have had n tosses, and now I want to compute the probability that the n plus first toss will also be a head, will show a head, and this is the expression. So, I am going to derive it for you. Since one of the k plus 1th coin will be selected, right. So, then f n can be written as f n union C I, because at least one of the coins. So, this probability of C I union C I varying from 0 to k will be 1, right. So, f n can be written as f n union I varying from 0 to k C I, and therefore, probability h conditional f n which is can be written as this, then from f n I can write this expression union f n intersection C I, right. And again by the distributive property of intersection and union, I get that this can be written as probability of union I from 0 to k h intersection f n intersection C I, right, because this is this. And then this, because you see all the C I's are mutually exclusive, right, because one of the coins will get selected. So, therefore, these events become mutually exclusive, and so the probability of the union can be written as sum of the probabilities I varying from 0 to k h intersection f n intersection C I divided by P f n. So, right. Now, this one I can write in terms of conditional probability as h condition f n intersection C I into probability f n intersection C I divided by P f n, right. Then this remains this. This again I can write in terms of conditional probability C I condition f n into P f n. So, P f n cancels because f n is a given event. So, therefore, probability f n cannot be 0, and so I get this expression which is written here, right. Okay. Now, it is reasonable to assume that repeated tosses of the ith coin are conditionally independent. This is where I am using the concept, that means repeated, to assume that the repeated tosses of the ith coin are conditionally independent with respect to f n. That means, see, I am considering the case when a coin was picked up randomly, then it resulted in n tosses showing heads, and now when I toss further, so then they will be independent of conditionally independent of f n, okay, which means that probability h condition f n intersection C I is actually probability h condition C I only. So, f n has no role to play here, right. This is what our definition of, remember we said that E 1 given E 2 intersection f. If I wanted to say that E 1 and E 2 are conditionally independent with respect to f, given that f has occurred, then this is probability E 1 f. That means, E 1 and E 2 are conditionally independent when f has occurred. So, then E 2 has no role to play on the occurrence of conditional happening of E 1 given f on the. So, the probability would be independent of the event E 2. So, the same thing here we are saying that here f n, because it is conditional on f n. So, this probability is has the f n has no role to play here, and so probability h given C I. So, this is what we are assuming here, and therefore, each of this probability is I by k, right. So, now that means I can now apply this in the formula here, and this is I by k. So, that means you are getting because you have got n heads have shown up, and probability of each head is I by k, and I am assuming that the tosses are conditionally independent. So, therefore, this is I by k raised to n, and the n plus first toss gives you a head will be 1 upon k plus 1, because there are k plus 1 coins there, and so sorry. So, this probability is what am I writing here? Yeah, C I f n. So, h given f n. So, let me just check out here. This is C I f n, right. So, a probability of picking up the ith coin. And so, again if you just pick up the ith coin, that probability should be 1 upon k plus 1, because any of these coins are equally independent. Remember, a coin is randomly selected. So, that means any of the coins is equally likely when you pick up from the box. So, therefore, the probability of picking up a coin is I by k plus 1. So, therefore, this becomes this, and similarly here. Yeah. So, actually what is happening is that C I f n, yes, I missed out on this part. So, probability C I given f n I have rewritten as this So, this is probability f n condition C I into P C I, and then this is sigma j varying from 0 to k f n. So, the probability f n I am writing in this way, f n condition C j into P C j. So, this is where, so now probability f n given C I, as since the things are conditionally independent, the probability of picking up a head remains the same. So, when you want to pick up n heads, this will be I by k raised to n, and probability C I will be 1 upon k plus 1, right. And then here similarly, this is summation. So, j varying from 0 to k, j by k raised to n, and 1 upon k plus 1, because now here your j is varying. This corresponded to the ith coin that you have chosen. So, this is the thing. And so, it is just a computation. I wanted to illustrate, maybe you can say that it is a engineered problem or whatever it is, but somehow you could make use of the concept of conditional independence and arrive at this result. And again, through methods of calculus, you can actually show that if k is large, then this probability is approximately equal to n plus 1 upon n plus 2. Okay. So, therefore, it gets simplified when you have a large number of coins in the box, but otherwise yeah. So, this were continuously you broke up the. So, here in this expression, yes, C I conditional f n, this also I had to rewrite in this decomposed form and then apply the probabilities to get this expression. So, that was missing here. Yeah, okay, fine. So, this is one, this is an example to and often there will be situations when you would be coming across the concept of conditional independence. Let me discuss exercise 2 with you. Again, I will just try to give you brief hints. So, anyway, probability, the question 1 says that you have to compute the probability that only exactly one of the events E and F occurs, and that is equal to probability E plus probability F minus 2. And of course, when we say minus 2 probability E f, that means E intersection F. So, that notation is also acceptable. You do not write the sign, the intersection sign, you simply say E f. So, that is what it means, right. Now, if E, F and G are 3 events, then you have to find expressions. So, again I am just wanting you to be familiar with how you express events in terms of your complements, union and intersection. So, here I want you to write find expressions for the events, so that of the 3 events E, F and G, only E occurs. So, if you have to write this, then in 2 you have to write exactly 2 of them occur, right, exactly 2 of them occur. So, the third one should not occur. So, you can imagine that you will have to use unions and complements, right. Now, in question 3, this is actually very simple. The slash sign, the condition sign is sort of dim, but anyway. So, this says that if probability A is greater than 0, then show that probability of A intersection B condition on A is greater than or equal to probability A intersection B condition on A union B. So, that is very straightforward actually. And now, you have to show that P of A intersection, the conditional probability of A intersection B given A is greater than or equal to probability of A intersection, conditional probability of A intersection B given that A union B has occurred. So, it is very simple, because you see A is a subset of A union B, and as we have already discussed, that probability of A union B will be greater than or equal to probability of A, right. And in the left hand side, when you compute the conditional probability, you will have A in the denominator, the numerator is probability A intersection B, because A intersection B intersection A is again A intersection B. So, this is what actually you have to figure out, and similarly on the right hand side, the numerator is the same, but denominator would be probability of A union B, and since probability A union B is bigger or equal to probability A, you have the required inequality. So, I just gave it to you to be able to just figure out these things, and therefore, then you can answer the question. So, if you write out the expressions, you can immediately give the answer to this question. Now, problem 4 is from Sheldon Ross, actually it should say Sheldon Ross or Ross Sheldon. In answering a question on a multiple choice test, where you have more than one choice and you have to tick the right one. A student either knows the answer or she guesses. Let P be the probability that she guesses. Assume that a student who guesses at the answer will be correct with probability 1 by m, where m is the number of multiple choices, right, because if she is guessing, she does not know. So, any answer out of the m choices, any one of them is equally likely. So, the probability is 1 by m. What is the conditional probability that a student knew the answer to a question given that she answered it correctly? And I have given the answer here. So, now what are we saying? What is the conditional? So, please enter probability. What is the conditional probability that a student knew the answer to a question given that she answered it correctly? So, use the concept of conditional probability and then you should be able to do it. Right. And now, again this problem is from Sheldon Ross. At a certain stage of a criminal investigation, the inspector in charge is 60% convinced of the guilt of a certain suspect. Okay. So, his conviction is that the 60%, that means 0.6 is the probability of the person being guilty. Now, suppose that a new piece of evidence shows that the criminal has a certain characteristic such as left-handedness, baldness, brown hair, etc. So, it turns out that through some eyewitness who may have seen the criminal doing the act, the eyewitness can only say that the person was either left-handed, one of the conditions characteristics is owned by the criminal. So, is uncovered. So, through some facts it is found out that whoever committed the crime has one of the characteristics, right. If 20% of the population possesses this characteristic, that means whoever in a town crime has taken place, and so what they are saying is that 20% of the population possesses this characteristic. How certain of the guilt of the suspect should the inspector now be? It should again, instead of how it should be now be, if it turns out again S, if it turns out that the suspect is among this group. So, now this is the situation for computing the base probability, because you see the first initially the inspector is 60% convinced of the guilt of a certain person. Now, it has been known that the criminal possessed some characteristic, which it turns out that this suspect has that characteristic. So, therefore, the probability of the suspect being a criminal would go up. And so, the posterior probability after knowing that the criminal possesses the characteristic will go up. So, therefore, you want to I want you to compute the posterior probability here. Problem 6 says a parallel system functions whenever at least one of the components work. Consider a parallel system of n components and suppose that each component independently works with population 1 by 2. Find the conditional probability that component 1 works given that the system is functioning. So, here you have to use concept of independence and conditional probability. So, problem 7 says that you have to either prove or give counter examples to the following statements, which are self-explanatory. You should be able to either show that the statement is valid, otherwise you construct examples to show that it is not. Now, problem 8, I am asking you to show that if E, F and G are independent, then you have to show that E is independent of F union G. See, remember now here I am using the definition of 3 events being independent. So, you have these 4 conditions that will be satisfied, and then you can easily show that E is independent of F union G. In fact, you can whatever subsets you find by operation of taking intersection, union or complement and then taking operations on those, you can show that E will be independent of any of that any of such event which is founded by which is obtained by doing the operations of intersection, complement and so on from F and G. So, this is what we are saying here. Now, store A, B and C have 50, 75 and 100 employees, and respectively 50, 60 and 70% of these are women, right. Okay. So, that means store A has 50 employees and of which 50% are women. So, you can immediately say that 25 are women, similarly 75. So, 60% of the employees in store B are women, and then 70% of the employees in store C are women, right. Resignations are equally likely among all employees regardless of sex. One employee resigns and this is a woman, what is the probability that she works in store C? So, now here again I am asking you to use Bayes formula to compute the probability. Okay. So, one employee resigns, that is given, and this is a woman. So, this is also given, that means a woman employee resigns, you have to find the probability that she works in store C. 10th, the probability that a new car battery functions for over 10,000 kilometers is 0.8. The probability that it functions for over 20,000 kilometers is 0.4, and the probability that it functions over 30,000 kilometers is 0.1. So, these are all conditional probabilities. If a new car battery is still working after 10,000 kilometers, what is the probability that its total life will exceed 20,000 kilometers? And then its additional life will exceed 20,000 kilometers. So, problem 10 we will have to answer, okay. Maybe we will leave out problem 10 from here and we will revisit it later on, but problem 11 you can answer easily. Suppose that a person chooses a letter at random from reserve. So, instead of chosen it should suppose that a person chooses a letter at random from reserve. That means, it can be any of the letters R, E, S, V, and then chooses one at random from vertical. What is the probability that the same letter is chosen? So, this of course, is your earlier from counting the probability the number of combinations that are favorable to this thing. That means, see the two letters that are common between these two words are R and E. That is it, right. So, you have to now find out the number of ways in which R will get selected from both or E will get selected. And you can see that, for example, in the first word reserve, R appears twice out of R E S E R V E, and R in vertical appears only once. So, you can accordingly find out the probabilities and then find out that, and since the operation of choosing a letter from reserve and from vertical are independent events, the required probability would be the product of these two. Okay.